Hello, students, and welcome. So, today we are going to tackle a very important topic from our unit on electrostatic potential and capacitance. Potential due to an electric dipole. I know this one sometimes feels a bit tricky, but don't worry, we're going to make it so simple that you'll never forget it. And everything we cover is straight from your NCERT book, so it's completely exam safe. Okay, so let's start with a fun question. Have you ever thought about this? How does a microwave heat up your food, but a small bird can just sit on a high-voltage power line and be completely fine? It's a bit strange, no? Well, the secret to both these things is something called an electric dipole, and that's exactly what we are going to master today. So the answer to our puzzle, it all starts with understanding the secret personality of a dipole. You see, it's not like a single charge at all. It has its own special nature. First things first, let's get the official definition from the textbook. What is an electric dipole? Simple. It's just a pair of equal and opposite charges. You have a plus Q and a minus Q, and they're separated by a very small distance, which we call 2A. That's it. Simple as that. But the real magic, the real secret of a dipole, isn't just that there are two charges. It's how they sort of work against each other. The main idea here is what I like to call the canceling effect. And to understand this, I have a really simple analogy for you. Just think about your noise-canceling headphones. How do they work? They create an opposite sound wave to cancel out the noise from outside, right? An electric dipole, it's doing something very similar. The negative charge is always working to cancel out the effect of its partner, the positive charge. So you can think of the plus Q and minus Q as a team, but they are working against each other. And because of this fight between them, their combined effect, their potential, it gets very weak, very fast as you move away. Their influence just fades away much quicker than a single, lonely charge. Okay, so now that we've got the main idea, this canceling effect, let's look at the official NCERT formula that puts this into math. This is the one you need for your exams, so pay close attention. Here's the diagram you'll see in your textbook. We have our dipole, minus Q, and plus Q. And we want to find the potential at some random point, P, which is at a distance r from the center. Now, look carefully at that angle, theta. This angle is super important because it tells us the direction of P with respect to the dipole. And here it is, the big formula. The potential, V, at that point P, is given by this expression. Please write this down. V equals 1 upon 4 pi epsilon naught multiplied by P cos theta upon r squared. This is equation 2.15 from your NCERT book, and trust me, it's the most important thing you need to know for this topic. Now, this formula looks a bit complicated, but it's actually made of three very simple parts. Let's break it down. First, we have P. This is the dipole moment, basically charge Q times the distance 2A. It's just a measure of the dipole's strength. Second, we have cos theta. This is the angle factor. It just tells us that the potential is different depending on which direction you're looking from. And third, and this is the most crucial part, look at the bottom. We have r squared. This confirms our canceling effect idea, right? The potential dies down very quickly with the square of the distance. Now, that cos theta might seem like a headache, but the good news is, for your exams, you only need to master two very special, very easy cases that come from this main formula. Let's check them out. So, here are the two important positions. Case 1 is the axial line. This is any point along the axis of the dipole itself. Here, the angle theta is 0 degrees. And since cos of 0 is 1, the potential is maximum. The second case is the equatorial line. This line is perpendicular to the dipole, right through its center. Here, theta is 90 degrees. And what is cos of 90? It's 0, so the potential is 0. Simple. And this brings us to a very common exam question. You must remember this point. On the equatorial line, the potential is 0 everywhere. But the electric field is not 0. Now, why is that? See, potential is about work done. On that line, any push from the positive charge is perfectly canceled by the pull from the negative charge in terms of work. So net work is 0, potential is 0. But the forces themselves, the field vectors, they are still there. They just add up in a way that creates a non-zero field. Okay, now everyone please pay full attention. I'm going to show you a very common trap in exams that makes students lose marks. But if you understand this now, you will never make this mistake. Just look at this comparison. For a single charge, we can call it a monopole, we learned that its potential, V, is proportional to 1 upon r. Just r. But for a dipole, because of that cancellation we talked about, the potential V is proportional to 1 upon r squared. This is the exact point where many students get confused and lose easy marks. So, I'm going to give you a simple trick to remember this for life. Ready? A dipole has how many charges? 2, right? So its potential depends on r to the power of 2. A dipole has 2 charges, so its potential depends on r squared. Simple, Hannah. Just write this down and you will never ever forget it. All right, so that was the main concept. Let's just do a quick summary so you can revise all the key points very easily before your exam. So let's recap the key takeaways. First, a dipole's potential happens because of a partial cancellation between the plus q and minus q. Second, the potential V depends on 2 things, the distance r and the angle theta. Third, and this is super important, the potential falls off very fast, proportional to 1 by r squared. And finally, for your exams, remember this. Potential is maximum on the axial line and it is 0 on the equatorial line. So now we understand how one single dipole behaves. But think about our first question, the microwave. It works because water molecules are actually tiny little electric dipoles. So what happens when you have trillions and trillions of these dipoles together inside a material like glass or plastic or even water, and then you put them in an electric field? Well, that question leads us directly to our next very important topic, dielectrics. We'll explore that in the next session. Thank you for joining.